ladies and gentlemen. I was introduced. Also, thank you. For everybody those don't know me, I'm also teacher at the university, and I strongly involved since 20 years in high-pressure pipeline maintenance, especially inline inspections. Coming to today's topic is steel pipeline failure probability of evaluation based on inspections, inline inspections data. To evaluate of external part wall metal losses, which I investigated, only external metal losses of the gas transmission pipeline being in service in Poland, I employed two methodologies, well-known methodologies. Also, first of all, code-based engineering approach to estimate the failure pressure of the pipe, of the defected pipe with active corrosion pits, also active corrosion defects. And the next step, I employed Monte Carlo simulation method to compute the pipeline failure probability due to pipeline burst with time. Coming back to the diagnostics data, so-called defect matching was employed, which was in detail discussed in the previous paper. We used actually defect matching for 138 external corrosion defects. It was actually so-called box matching. The study considered in this presentation are based on two repeated inline inspections conducted in the year 2000 and 12 years later, also 2012. And defect growth rates, also corrosion velocity, was based on a defect matching, and there were experimental mean values for these 138 external inline inspection indications. Here you can show the depth, relative depth of external defects of the studied external defect distribution. The red is the data derived from the first inspection, and the blue, the second inspection. The defect depth was assumed as a normal distribution with certain error expressed in coefficient on variation, also in standard deviation and mean value actually. Here are shown the special defect depth scopes, also up to 10% of wall thickness, between 10% and 20%, between 20 and 30, and so on. And the deepest defects are located in this scope between 30 and 40% of wall thickness of the studied pipeline. Here are shown the defect length distributions from 2 inspections, and also red from the first inspection and the blue from the second inspection. And in our case, they are fitted to the log normal distribution with certain variations, also coefficient of variation, mean and standard deviation. Also, the longest external corrosion depth, where with this scope also up to 180 millimeter, also up to 20 centimeter, circa. We have employed the well-known DNV recommended practice to calculate the burst pressure of the pipeline with corrosion defect, which the depth of the corrosion is shown here as a maximum depth, and TS wall thickness, and the other parameters as defect length, pipeline outside diameter, and material ultimate strength was treated as uncertain values. The flaws, as can we derive from the inline inspection data, has a residual wall thickness breach. Also, here can be shown here. Also, there were only part wall defects, and we don't apply the criteria for defect depth exceeding 80% of wall thickness. Here's the visualization of the typical shallow corrosion, which are typical for this investigated pipeline. In general, a steel pipeline fails by either a small leak or a rupture. And the main internal, also the main force or the main loads is internal pressure taken into consideration as a random variable with certain distribution. Also, here on photo, you can see the typical leak and the typical crack, also the defect-like crack, also which can be considered as a rupture of the pipeline with certain amount of leakage of the gas to the surrounding. In this investigation, as I mentioned before, was only pipeline rupture considered, because also due to the cost of small leak is much more insignificant compared to the burst consequences. Coming back to the corrosion velocity, which is necessary to assess the pipeline reliability with time. As it was said in a previous presentation, the corrosion should be highly variable along the distance of the pipeline, and it depends on many factors, such as soil conditions, such as other variables. In our study, also in my study, it was applied the corrosion rate determination using 2 repeated inline inspections data sets. Also, it can be called as experimental mean values in this presentation, also in this research, for 2 repeated derived from 2 inline inspections. The model of corrosion growth in depth, also in radial direction, was described by this equation, which is in the literature called as a power law function, with depth, initial depth as a mean value, and this 2 pitting proportionality and pitting exponential factor, also the key and n. They are obtained by statistical studies of many pipelines. And in case of this pipeline, of the studied pipeline, this equation would be suitable. Also was selected as an appropriate equation to evaluate the pipeline corrosion velocity in radial direction. And here's a plot of this equation with time, with 60 years of operation. Predicted defect dimensions in axial direction were made in 4 scenarios. We studied the axial corrosion, actually. It can be called axial corrosion. With this, here described described by this equation, mean length of the defects derived from 2 repeated inline inspection with time, with base time, also with start of this analysis, and then the second factor is the actually axial corrosion growth rate in different in 4 scenarios. As a base scenario, 1.8 millimeter per year, and second scenario 1 millimeter per year, third scenario 0.5 millimeter per year, and fourth scenario, no defect growth in axial direction. Also, only defect growth in radial direction. And the considered scenarios you can see here, the base scenario and the rest 3 scenarios of corrosion growth. As I mentioned before, there are experimental values, and this based on 2 inspections. However, this scenario was introduced for analytical reasons. To calculate the pipeline failure probability, it is necessary to introduce a limit state function, and is commonly used in the literature the limit state function, which is difference pressure limit state function, which is shown here. Also pipeline burst pressure. In this research, according to the standard DNV recommended practice, minus uncertain operating pressure. Uncertain, it means that it has a special, also certain this statistical distribution. And the solution of this equation, which is found, also failure probability for the corroded pipeline, also the pipe with active corrosion as a function of time. Time can be expressed as probability that G function. This is below less than 0. And since here many analytical solutions of this function were found, I applied in my research Monte Carlo method, in which the failure occurs when this G function is less than 0, and the certain trials of the input values was set, and then the occurrence of function below 0 is counted, and the pipeline failure probability is calculated according to as a function of time, T is time, is calculated according to this equation, also 1 minus multiplication of this formula for every individual defects at specific time step. And the failure probability is compared to the code-based target probabilities, which depends on the so-called pipeline safety class. Safety class low, the probability is 10 minus 3, and for the safety class normal minus 10, 4, and per annum, and for the high safety class 10 minus 5 per annum. It is code-based, derived from DNV recommended practice. Coming back to the load of the pipeline, the only load which was considered, also applied, was the pressure, internal pressure, and we introduced the pressure fluctuations described by so-called extreme value distribution, known from the literature as Gumbel distribution, which parameters are location and scale, and the distribution of pressure, internal pressure, in case of our pipelines, resulting from the unsteady flow is shown here. Also, the mean value of this distribution of this internal pressure, gas internal pressure, is 5.5 megapascal, and here you can see the parameters of Gumbel distributions. Also, the pressure for most of the time is not exceeding 6 megapascal at certain probability of occurrence. And here is the table showing all of the parameters taken into consideration in my research. Steel yield strength, which is necessary according to the DNV standard, which is based on the tensile strength. Also, actually, this value is more important in this research. And these uncertainty coefficients, coefficient on variation and standard deviation, were derived from the manufacturer of pipes, data from manufacturer of pipes of this pipeline. And the same is with pipe wall thickness. The nominal wall thickness, also mean value, is 11 millimeter, and the standard deviation 0.45, and coefficient of variation 45.5%, and it has normal distribution. Tensile strength has long normal distributions. Pipe diameter outside is 711 and is also normal distributed. Maximum pressure, I introduce it, and is Gumbel distribution, and there are the parameters. Defect depth mean value derived from repeated inline inspection is 2.2 millimeter, and standard deviations 0.6, and coefficient on variation 26.6%, and it has normal distribution. Defect length has a mean value 35 millimeter, and here are the parameters of log normal distributions, and defect grow rate and defect depth, length grow rate, defect depth grow rate, and length velocity I discussed before. Also, here is the statistical plot of the burst pressure change over time for power law function, which was applied in this research, and defect length grow rate of 1 millimeter per year. And here's the 50% of probability chart, yeah, and also during the 60 years of pipeline operation, the prediction shows that the burst pressure, calculated according to the DNV standard, decreases from 70.5 megapascal to 13.5 megapascal with a chance of 50%. Also, this is uncertain calculations, and this value are given with certain value of probability or the certain value of chance. And the failure pressure or burst pressure or rupture pressure of the studied pipeline over the 60 years of operation of this pipeline was shown here. It depends on the defect length grow rate. And for scenario 2, the mean value of the burst pressure is about 13.5, and when it is for scenario 2, for scenario 3, The mean value is 13.5, and for no defect grow length, also 0 defect grow length in axial direction is the biggest value, about also circa 16 megapascal. Also, from here can we derive that the burst pressure within the time depends on defect length growth rate. And coming to the probability calculation, which is topic of my presentation, here is shown the computed failure probability over 60 years of pipeline maintenance, and for many years until 5 years of pipeline operating after the diagnostic, after the second diagnostic, the failure probability is very low, and after the 15th year, the failure curve, also the failure probability curve here for the scenario 1. These equations are for scenario 1. Also, when the defect depth is described by power law function and defect length has the highest value described by this equation, we can show the rapid aging process of this pipeline, which is typical for the underground assets affected by corrosion. And in 55 year of pipeline operation, it is crossing the target failure probability. This is this point set in DNV for high consequence areas, also for safety class high. And here you can see the other scenarios of defects length probabilities curves, and this is for scenario 2, this green, and in this case the target probability is reached in the 59th year of pipeline service. Coming to the conclusion, also a decrease in the burst pressure of the steel pipeline considered as a rupture depends first of all on the defect length growth rates, mean values, as was said in or also shown in this presentation, as well as a defect depth velocity during the service of a buried pipeline. For scenario 1 of the features dimensions change with time, the most significant defects localized on high safety class segments of the pipeline needs to be repaired to avoid to reaching the target failure probability in case of this pipeline. The calculations of the onshore pipeline failure probability based on magnetic flux linkage inspection results are helpful to maintain their values within the standardized acceptable scope, as it was shown in my presentation. The presented methodology is a technique for underground asset reliability control and for extension of remaining service life of pipelines with active corrosion. Thank you for the attention, and please do not hesitate to ask any question.